Welcome dear students. In this video lecture we are going to discuss the two important parameters in regards with the fin. In previous three lectures we derived the temperature distributions as well as the rate of heat transfer from the different configurations of fins. Let us summarize all the three cases and then we start with our today's topic. First case that we discuss, infinite long. In that temperature distributions we get in dimensionless term that theta by theta naught equals to e to the power minus mx. Using this equation we are able to calculate the temperature at any sections or at any length of the fin. Then the rate of heat transfer q fin we get m into theta naught, where the theta naught or the theta is only the temperature difference T minus T infinite, and m is stands for the under root of we can write that hp upon acs into k. So in second case we discuss the adiabatic heat transfer, means the heat which cannot be transferred at the tip of the fin. In another word we can say that it is an insulated fin. So in that temperature distribution we get theta by theta naught equals to cos hyperbolic m L minus x upon cos hyperbolic ml, and the rate of heat transfer, that is q fin, we get m theta naught into tan hyperbolic ml. And third case, that heat loose from the tip of the fin, it means the convective heat transfer at the end of the fin, we get cos hyperbolic m into bracket L minus x plus h by mk sin hyperbolic m L minus x divided by cos ml plus h by mk into sin hyperbolic ml. Similarly, a q fin in case of the convective heat transfer, it means the heat losing from the tip, that m into theta into sin hyperbolic ml plus h by mk into cos hyperbolic ml divided by cos hyperbolic ml plus h by mk into sin hyperbolic ml. So this is a summary of previous three lectures. Now we are going to discuss the important parameters or the today's topic, that is the effectiveness of fin and fin efficiency. So first we discuss the fin efficiency and then we are going for the derivations of effectiveness of fin in all the three cases. The main purpose of applying fin is to enhance the heat transfer. If you remember, in earlier cases we discussed that the heat transfer by the convection, that is q equals to h a delta t. If your h is very small, your area is insufficient or it is inadequate to remove the larger amount of heat, then and then we apply the fin. So let us check that whether the applications of fin is justified to enhance the rate of heat transfer, or we can add the more amount of cost, more amount of weight, and we are generating the complexity on the surfaces. So we have to check that by applying a fin, our efficiency is there or effectiveness is there for the considerations of rate of heat transfer or not. So let us go with these two performance parameter for the fin. So first is the efficiency. Let us check the efficiency. What is the concept of efficiency of fin? So if you remember, in all the three cases of fin, that the temperatures is dropped as you are progressing in the length of the fin. Suppose I am taking one example, that base temperature is 80 in this case, and as you progress at certain point the temperature is become 70, here it is 65, here it is 61, 58 and 56. So temperature progressively decreases, but if you assume your conductivity, that K is very infinite, it means there is less resistance or resistance is near to zero, thermal resistance, then the temperature drop on the fin surface is becomes zero and you get the constant temperature on the fin surfaces. It means the rate of heat transfer from fin to the ambient, let's say is in this case, as you are progressing your convective heat transfer rate is decreases because Ts minus T infinite is decreases, where in this case your Ts minus T infinite is becomes a constant. because your temperature on the fin surface remains a constant. So using these two concepts, one is called as ideal concept and second is actual. It means we are assuming there is infinite amount of thermal conductivity and your thermal resistance becomes a zero. So let us, on the basis of that, we can define the efficiency of fin. Efficiency is indicated by eta and we are indicating for the fin. So eta fin equals to q fin, that is actual, divided by the ideal one. It means we can write as q maximum. So the definition of fin efficiency is the ratio of the actual heat transfer by the fin to the maximum heat transfer by the fin. It means here, in another word, we can write that the q fin divided by q fin, but considerations of k tends to infinite. So you need to remember these words, that, and I repeat the definitions. The efficiency of fin is defined as the rate of heat transfer from fin to the maximum heat transfer by fin. Now we go for the case number 1. Our case 1 is for the infinite long. So if you remember the formula of infinite long fin, we are going for case 1, that the infinitely long fin, in another words, L tends to infinite. So eta fin in this case becomes q fin divided by q fin max, or we can write as q max. So q max is only the convections. If you go for the q max means there is no conductions happening because the thermal conduction resistance is zero. The heat transfer from the fin is only happening by the convections. So in this case, the q maximum becomes the perimeter into the length, that is your area, this is the surface area, into temperature difference, that is T naught. Base temperature is T naught and the infinite temperature, that is bulk fluid temperature. So in all the cases, the maximum amount of heat transfer becomes HA delta T, because there is no conductions, because there is no temperature drops. So only heat is transferred from the fin surfaces by means of only the convections. So H into surface area, that becomes a perimeter into the length. T naught, there is a constant temperature on the fin surfaces, and infinite, that is a temperature of air. So now we can get this q fin in the case of the infinite long fin, that under root of HPACS into K into T naught minus T infinite divided by the q maximum, that is H P into L T naught minus T infinite. So by simplifications, we get the under root of the HPACS into K divided by H square P square L square. We get this, and if we simplify it further, we get efficiency of fin in case of infinite long fin 1 upon ml. So it comes as a dimensionless, and it is also because this is we know that m fin constant having a unit of meter inverse and multiplied with the length, it give you the unitless terms. So in second case, if we go for the second case, that fin is insulated, tip of fin insulated. So in this case, q fin becomes under root of HPACSK T naught minus T infinite into 10 hyperbolic ml divided by H dot PL into T naught minus T infinite. So by simplifications we get the q fin in the case number 2, that is equals to tan hyperbolic ml divided by ml. So this is our two expression which is very important for solving the numerical as well as this kind of questions is asked in our university examinations. So now we have to go for the conclusion. So from this discussion we can conclude that the performance or the efficiency of fin is depends on the perimeter as well as the length of fin. So if you are increasing the length of the fin, definitely the weight is increases. So for the space applications we have to go with a perimeter. It means the geometry having a larger perimeter is very useful in case of the space applications. But if beyond certain limits of the length we cannot be able to justify the effectiveness or the efficiency of the length, so for that we need to go for the various geometry. And if we discuss the geometry like a triangular, then a parabolic, then it has a very high geometry. It means a perimeter of this kind of geometry is very high compared to the other geometries. So here restrictions means designing of fin is considered the two parameter based on the efficiency of fin, that is perimeter and the length. So now we are going for another very important performance parameter, that is the fin effectiveness. The two different concepts that we are going, it means the performance parameter that we discussed, there is a two performance parameter, one is efficiency and second one is effectiveness. When we are going to design the fin, it is only the purpose to enhance the rate of heat transfer, and the use of fin on a surface cannot be recommended unless the actual enhancement in the heat transfer is justified. It means the purpose, if the purpose is not so, then there is no requirement of fin. So similarly we have to go and we have to check that effectiveness of fin, and this performance parameter is very important, because if the enhancement of heat transfer is not justified, then we only added the cost and we also generate the complexity associated with the fins. There is no assurance that by adding the fin you can have enhanced the rate of heat transfer. It means by applying only the simply fin you cannot be able to justify that the fin or the enhancement of the heat transfer is happening because of only the fin. So in this case we need to go with the effectiveness, and effectiveness is a very important parameter to check that your fin is effective or not. So for that we need to go and we need to understand what is exactly the definition of effectiveness, and from that we can able to justify it, or we can write, or we can conclude the few parameters or the few assumption in regards with enhancement of heat transfer from the fin. So fin effectiveness we can understand from the figure. The case 1, there is no fin, there is a q dot no fin. And second, when same base area, here I can take the circular cross section. So the circular cross section there is no fin, and the fin which is having a circular cross section I have fitted over on this area. So effectiveness can be defined, that effectiveness is indicating by E, that effectiveness. From the figure we can understand the Q means rate of heat transfer with fin divided by Q without fin. Means the heat transfer from the wetted area by the convections without any fin, and when you have applied the fin you have to calculate. So from this area the heat transfer occurs according to the convection only, and we know the formula. The area of base is QAB, or area, simple area we are taking, there is a cross sectional area of the fin, both are same. So we write Q without fin which is equals to the H, then cross sectional area, then T base, it means T naught, and in the T infinite. So we get this. So now we calculate the effectiveness of the fin in case of finite length or infinite length, both the cases. So we are going for infinitely long fin. So effectiveness of fin equals to Q fin and Q without fin. So by putting down the value, we get Q fin for the finite long under root of H P ACS K T naught minus T infinite divided by Q without fin, that is H ACS T naught minus T infinite. So it is cancel it out, and finally we get the under root of P into K divided by H into ACS. Similarly, we can write the formula for the fin with tip of fin insulated. So effectiveness of fin equals to Q fin, it is under root of HP ACS K into T naught minus T infinite into tan hyperbolic ml divided by the H ACS T naught minus T infinite. So we get the under root of P dot K upon H into ACS into tan hyperbolic ml. So these two expressions are very important. But now we are going to discuss the conclusive remarks on the effectiveness of fin. So from these two equations, if we give the name, that equation number 1, so we can discuss the equation number 1 in depth. So effectiveness of fin is the under root of P into K upon H into ACS. So we can write some conclusion or conclusive remarks from the effectiveness. The first remark that we write, the fin is only effective when your K, the thermal conductivity, is high. It means the material of the fin may be used which is having a higher thermal conductivity. So if we discuss the metal, then copper and aluminum and other metals, because metals having a free electrons, and due to that the thermal conductivity of metal is higher. As well as if we discuss about the corrosion resistance and the lighter weight, then the copper and aluminums are very good. It is very good material for the fin. Second things, fin is only used when your H is small. It means from this expression we cannot be justified the fin in which the H for the liquid is very high, as well as we cannot justify the H for the force convections. It means the fin is only effective when the medium or the convective heat transfer medium is gas. It means air or any gases. and in natural convections it is very suitable. So this is a second conclusion from this effectiveness of fin. The third is very important. The P by ACS ratio, the ratio of perimeter to the cross sectional area is increases, it effectiveness is also increases. From this all the three we can finally conclude that our fin can be effective in only the three conditions. One is when the fin material having a higher thermal conductivity, and fin is effective in only cases when your convective heat transfer coefficient is very less, or we cannot suggest the applications of fin in case of forced convections, or your material for the convections or the medium for the convection is liquid. And third is the fin effectiveness is increases as the ratio of perimeter to the cross sectional area is increases. Second thing here, the fin is only justified where your effectiveness is becomes a 1 when there is no fin. It means the effectiveness is becomes a 1. So we expect the effectiveness of fin is always greater than or equals to 2. Then and then we can justify the fin. So this is the two important parameters that today we learn in regards with the fin, that effectiveness and efficiency. So thank you for attending this lecture.